This is problem set 3, exercise 2. Now we're going to solve the same problem that we solved in the previous exercise, in exercise 1, but in this case we are going to use the technique used with the Barabasi-Albert model, the one that we saw in the theoretical part of this course. Okay, so now instead of using a master equation, what we are going to do, we are going to solve, we are going to use instead of discrete time, we are going to use continuous time, and when we are going to assume that the derivative of the degree, of the in-degree of each node with respect to t is going to be z times the probability of this node of obtaining a new link, sorry. So this is what we're going to do, and this probability is going to be the same one that we used in the previous exercise. So this probability is equal to ki plus a divided by, now I'm going to write t instead of n, because in this case we are going to use t, okay, because it's continuous time. So for me it's quite it's quite difficult to write the derivative with respect to n, although it is possible, but in my mind n is a discrete number, so it's difficult for me to do that. So that is why we are going to assume that now t is the number of nodes. So it's exactly as before, but we are assuming that nodes are arriving continuously, okay? So we, instead of one node at each time step, we are going to have that nodes are arriving in a continuous way, which is not easy to understand, but in the end, we are going to see that it works, because this equation, it actually works. So let's solve this equation, okay? Remember that we have to take into account that the initial condition of each of these nodes when a node arrives at time t, so node I arrives at time ti, okay, with degree 0. In this case we have 0, well, with in degree, sorry, with this is in degree 0. Okay, so remember that in the Barabasi-Albert model, we were dealing with an undirected network, and nodes arrived with m links. So the initial condition was m. In this case, a node arrives with not m but z outgoing links, but the initial in degree is 0, okay? And that is why we have to include this number here, this parameter. So we are going to solve this equation. And what we're going to do, well, we are going to separate variables, so we can write the part that depends on k, which is the differential of ki divided by this part over here, and then this differential of t, I'm going to write it on the right side. That is what I'm going to do. So what we find is that differential of ki over ki plus a, this is equal to z over z plus a times differential of t divided by t. And now we are going to integrate this expression. So when we integrate on the left-hand side, what we obtain is the logarithm, okay? Remember that we have differential of the variable divided by the variable plus a constant, then this is the logarithm of the variable plus the constant. And this is equal to this part over here is a constant, okay? So this part over here is just a constant, and then here we have, I forgot to write the absolute value of this thing, and this is going to be z over z plus a logarithm of the absolute value of t. Okay, so that's the idea. And I forgot the constant, sorry. Well, in this case, since everything is greater than 0, because the in degree is always going to be greater than 0, a is greater than 0, and time is also greater than 0, this is, the absolute value is not necessary. So what we're going to do is just, when I do the exponentials now, Well, we know that even if there were any negative value, it would be included in the next part, okay? But from here, I just do the exponentials on both sides, and what I obtain is that ki plus a is equal to some constant a, I'm going to call this constant a, which is the exponential of c, times, well, this part over here, yes, this part over here is the logarithm of t to the power of z over z plus a. So this is what I'm going to write now. So this is, when I do the exponential of this part, this is just t. I'm just going to write t because the absolute value of t, like I say, is just t, okay, to the power of z over z plus a. And if I divide everything by z, then this is going to be the same as a to the power of t times 1 plus divided by 1 plus a divided by z, okay? And you can see that this element here appeared in the previous exercise, so that's not a bad thing. This is the expression of k in terms of t. Okay, so remember now that for t, when t is equal to ti, okay, the in degree has to be equal to 0. So this is the way to obtain the value of the constant. So we know that when at t equal ti, we know that ki is equal to 0. So we find that from this expression, from the previous expression, I find that a is equal to capital A times ti, because now I'm at time ti, okay, so that's the point, to the power of 1 over 1 plus a over z. So capital A is equal to lowercase a times the same exponent but with a minus sign. So it's going to be exactly the same but with a minus sign because it is dividing. So this is the value of a. So in the end, when I substitute this value of a in the expression of ki, what I obtain is that ki is equal to minus a plus a, and this part here we have a t to the power of some exponent, and here we have ti to the power of minus some exponent. So it's exactly the same. It's just t over ti, okay, exactly the same exponent. So in the end, I just have to write like this. One is dividing and the other one is multiplying. So it's just like this. I can also rewrite this expression taking as a common factor a. So I'm going to write this like t over ti to the power of 1 over 1 plus a over z minus 1. And this would be the final expression of ki, of the in degree in terms of the initial time and also the ending time. So let's see how this expression works. We see that this expression, when we fix ti, okay, this is increasing in t. Increasing in t for fixed ti. Meaning that once a node is born, then the in degree is going to increase with time. That's what it means. But it's also decreasing in ti for fixed t. So for the first part, the part where we know that ki is increasing with t for fixed ti, we have something like this, okay? We have something like this, more or less. So this is for fixed ti. So and this is equal to ti really, okay? So this is ti because it's 0 at when a node is born. So this is not 0 really, but ti. So when a node, so instead of writing it like this, okay, instead of the plot like this, I should do something more realistic, okay, something like this. My mistake. Something like this. So starting from some ti, we are going to find something like this. That's it. And this is for fixed ti. Now, this is the 0. And now for fixed t, we are going to find something like this. It's something which is decreasing instead of increasing. Now this is in terms of ti, and what we find is that as ti approaches to 0, this is going to diverge. Okay, so this is going to be larger and larger. And at ti equal to t, we are going to find that this expression is going to be 1. So 1 to the power of 1 is 1, to the power of whatever is 1, and 1 minus 1 is 0. So what we find is that when ti is equal to t, then this has to be equal to 0. So for fixed t, okay, what we have is something like this, something which decreases and goes something like this, more or less, okay? I don't know if this is exactly the way that it works, but it's going to be something similar to this. And this is for fixed t. And this means that instead of, in the left case, here we're focusing in just one node. We are focusing in one node that was born at time ti, and then the degree evolves with time. That's what we're dealing with here. But in this case, we are fixing t. And we're focusing in all the nodes that have that were born before time t. Okay, this is what we're dealing with here. So in this case, what we find is that all the nodes that were born before this time, they have this in degree. Okay, so depending on the time they were born, okay, depending on this time, they are going to have a specific degree. So if we want to know the probability of finding a node in the network with in degree greater than k, okay, then if we fixed here a value of capital K, okay, if we fix this capital K here, then we just have to look at this curve, and at this point, okay, this is going to be the degree that that should have a node that was born at some time tau. Okay, so that's the idea. So all the nodes, because this is at fixed time t. Okay, so all nodes which have a degree which is greater than k, okay, if we are focusing on this part here, then they must have been born in this time here, okay? So before that time, because we have that the degree is decreasing with ti. So what we have to deal with, we have to look for nodes that were born before this time tau. And this time tau is just, we can find this time tau from this formula, because if instead of ki I write capital K here, and here I find the ti such that this is equal to capital K, this value is equal to capital K, then that's it, that's the value that I'm looking for, okay? And if instead of looking at the nodes with in degree greater than k, we are looking at nodes with in degree less than capital K, then it would be something really similar. In this case, instead of looking at, the nodes with degree less than capital K would be here, okay? So those are these nodes here, okay? Those are the nodes that correspond to this curve. So we have to look for this fraction of nodes. Remember that the total number of nodes is t. Okay, so if the total number of nodes is t, then this part over here is going to give me the fraction of nodes with degree greater than some specific k, and this part over here is going to give me the nodes that are going to be in this part. Okay, so these are the nodes with ki greater than k. We cannot see this very well. I'm going to remove this part. So this is ki greater than capital K, okay, this is tau, and these are the nodes, the portion of nodes where ki is less than capital K, okay? We are going to find what this tau is in terms of k, because from this probability we are going to obtain the density distribution, okay? So the probability density is going to be just the derivative of this cumulative distribution, okay, the probability that Ki is smaller than capital K with respect to capital K. So this is the density. This is the definition of the density. Remember this, okay? So that's it. So what are these two quantities in terms of tau? What are these two quantities in terms of tau? Well, in terms of tau, like we have just seen, this part here is just the fraction of nodes that were born before tau, which are tau, okay, tau over t. This is that's that fraction, okay? So we have tau over t. But if instead of that quantity, I want to look at that quantity, which is the one that I'm interested in, this is 1 minus that fraction of nodes, okay? Because they are complementary. They are complementary quantities. So in the end, remember that the addition of these two quantities has to be equal to 1. That's it, okay? So that is what we are going to use in order to find this probability distribution. Now, I have to find tau, so let's find out tau, because we are going to use this formula, okay? And then we are going to use this formula. But first of all, I need to know what is tau, and I'm going to find tau in terms of capital K. So that's what we're going to do. We are going to use this expression here that we found before, okay? And from this expression, we are going to find what Ti is going to give me capital K. That's the idea. So capital K must be equal to lowercase a times T over tau to the power of 1 over 1 plus a over z minus 1. So this is the tau that is going to give me that. So let's find out what this tau is its value. I mean the value of this tau. So I'm going to write this like I'm going to clear the value of tau. So K over a plus 1 has to be equal to T over tau to the power of 1 over 1 plus a over z. And then I'm going to clear the value of tau. So, I'm going to do the power of K over a plus 1 to the power of 1 plus a over z is going to be equal to T over tau, and therefore tau is going to be equal to T times this exponential here, but with a negative sign because it's going to the right side dividing. So this is just K over a plus 1 to the power of minus 1 plus a over z. So this is the value of tau that we obtain. And with this value of tau, now I can substitute here in this expression, okay? So I'm going to obtain this probability. So the probability of finding a node within degree less than capital K is going to be equal to 1 minus, and then tau over T is going to be just, tau over T is just going to be this without this T. So it's going to be this expression here, tau over T, okay? So I have just K over a plus 1 to the power of minus 1 plus a over z. And that's it. Once I have this expression, now I can find out what is the value of the probability density. Remember that it's just the derivative of this cumulative probability with respect to capital K. So that's what we are going to do. In fact, what I can do is to write this in terms of just a simple K, not a capital K, and that's it, but it's okay. So I'm going to do the derivative of this with respect to capital K. So pk, which is the derivative of this expression with respect to capital K, this is going to be equal to minus, this is a power, okay? So I have the base to the power of, so if I do the derivative with respect to x of x to the power of n, this is n times x to the power of n minus 1. So in this case, x is all this part here, this is x, and then this is n. So that's what I have to do. Since x, okay, so I have to do after that the derivative of this part, okay, because this is a compound function, composite, I don't know. So I have the minus part of this minus here, I have this minus here, but I have to multiply it by n, so I'm going to find that this is just exactly the same as plus 1 plus a over z times this k over a plus 1 to the power of this power here minus 1, which is just minus 2 plus a over z, and then multiply by the derivative of this with respect to k, which is 1 over a. Okay, so this is the probability distribution that we are going to obtain in the end. I'm going to rewrite this in terms of a lowercase k instead of capital K, but it's exactly the same as before. So, and I'm going to order this a little bit. So I'm going to find that this is, well, it's just the same. It's just 1 over a times 1 plus a over z times k over a plus 1 to the power of minus 2 plus a over z. And if you compare, this is the final expression, okay? And if you compare this expression with the expression that we obtained in the previous exercise, we're going to find out that it's exactly the same. So we obtained the same expression with two different approaches. The first approach, we dealt with master equations in discrete time and also with discrete degree. In this case, we are dealing with a continuous time approach and also a continuous degree approach. So it's completely different. They are completely different approaches. But even so, they are completely different. We obtain the same result, which is quite robust. Okay, so that's a good result.